It's out of the way. I'm gonna leave it in position, Gina. I'm not gonna move it. But you can do whatever you want.
I just heard like.
You be you.
I just took a picture and then rotated it.
I know, I saw. I mean, I didn't see in the beginning, that's for sure. All right, so we have 2K down. The only other force going up is AY. That's gotta be 2K. So that's the first one. You can write that equation, or if you just see it by observation, that's fine too. So the equation forces in the Y would be a plus AY and a minus 2K equals 0, and then AY equals 2K. Okay, once you get that, you can see that joint A is a clean T. Boom, boom. So AB, that member, is 2K. But we can prove that by doing a joint analysis later. Moments at B will give you AX. So moments at B, right here, AX times 10. And also that rotation is plus, and then 2K times 5, and that rotation is minus, so it equals 0. 8x equals 10 divided by 10, which equals 1. Yep. So AY 2K, AX 1K, that makes BY 1K. So now we have all the reactions solved out. That you have to do first before you get the members. Then you can do joint analysis. So I went to pin A or joint A because it's pretty easy. Looks like this.
Easy for you.
Joint A, come on. You got to admit that looks pretty easy. 2K up, 2K down, 1K and 1K, and that solves two of the members. So AC is this, and it equals 1K, and AB equals 2K. And they both point away from the connection. So they are in tension. Don't forget to give me that. Some of you forgot to give me that. So that just, yeah.
It was a little funny that I got 0K in tension.
I know. I was like, didn't that disturb you?
Yeah.
It was funny. No, not funny, but kind of engineering funny. So then we need BC. You can go to C to get it, or you can go to B to get it. Doesn't matter which one. I think I went to B.
After I submitted a quiz, I realized that I put the AX backwards.
You and Gina.
I was
Both.
like, oh, damn, I forgot.
And then some of you were like,
Wait, you marked it wrong.
oh, I hacked it in the beginning, and then I went back and regraded it once I realized what you did.
Thank you.
Yeah,
You're
I
welcome.
went like,
Appreciate
I
it.
did it wrong.
Somebody else took this AY and put it here, which it is, I get that, but it was really weird. Like,
I know.
I'm like, okay, it's a roller at B. Why is AY down there? But it's legit because you can move these forces anywhere along their line of action. So it really didn't change the problem other than make point B a little crazy. Anyway, 1K in. We have AB, which is 2K away. And then this force of BC coming in. It's got to come in because 2K goes away. So that is going to put BC in compression. And we just need to figure it out. This becomes a right triangle, is how I did it. So that gets drawn like that, with this being BC, this being 1K, this being 2K. And then since we really just need this load, I just did pathetic right there. BC is gonna equal the square root of 1 squared plus 2 squared. BC equals 2.24 K compression. All right. Overall good. Everyone pretty much attacked it correctly. Some little mistakes here and there. Homework. 10 and 11.
Yeah.
Yeah, that was 10. I
That
hope.
was interesting.
I hope it's 10.
Yeah, it is. Then
Okay, good. I drew the right one. I'm always afraid I'm gonna draw the wrong one. What do we get for the reactions?
X is 5.
EX? Is there, where's the 5K at? Did I not get it? Oh, there it is. Yeah, I forgot it. Thank you. That is true then. 5 kilonewtons, so EX would have to be 5 kilonewtons. Then what do we get for AY and E?
Yeah, why?
Yeah, I got
Hey,
it.
why?
I got 6.
72.18.
For AY?
7
Well, I got 17.
Wait, what?
The engineering firm.
The engineering
Hey,
firm is
AY.
really shaky right now.
I didn't say
AY, I got
fast.
70 point,
Friday.
Okay, clearly we need to do this, so let's do it. What'd you get for AY?
72.19.
Oh, that's becoming popular.
So I was, yeah, I
Yeah.
checked that, you said that was.
All right, so let's go some,
got it wrong.
so hopefully you get some a moment about E to get AY.
Yeah.
Yeah, okay. So a moment about here, and I'll put AY in the equation right away. AY times 1, 2, 3, 4 times 4 is 16. Yup. Rotation. Negative.
Yeah.
Okay, that's good. And then it's 45 times this one, 1, 2, 3, 12. Positive. 60 times 8. Positive. 30 times 4. Positive. 5 times 3 is positive. Yeah. And nothing else about 0.8. We did them all. AY 45, 60, 30, and 5. AY 45, 60, 30, and 5. Set it equal to 0 and solve for AY. This is how the solutions are given to us. What number is this? 10? So notice they put in RA, EV, EH, horizontal, vertical. Yeah, isn't that interesting?
Yeah, reaction.
Yeah, reaction today. So they labeled it R. Yeah. But then they really don't solve it. They just come down here and get to this. Oh, yeah, they did right there. All right, 72.19. Yeah, they round. 72.18, what? 75 kilonewtons. And then they stop with reactions because they do their section and then they use that side. Just to show you how the book does it. So we could go ahead and get that other reaction because we know 45 comes down, 60 comes down, 30 comes down. So that's 135 down, right? And 72 up. So EY's got to be the difference between that. Again, if you're gonna section it and just use the left side, you don't need that and you don't need that. Right? So it depends on which half you're using.
Yeah, make two. Did you say that?
Huh?
Didn't it say you had to make two?
Yeah, but you could then use the left side both on both cuts
Oh,
or the right side on both cuts. So, but 135, 72, 1875. 62, 81, 25. Is that right?
yeah.
Anybody else get that?
Yeah.
Okay. So there's our reactions, 72, 4, 1, 8, 7, 5.
What you do for forces of the Y?
Forces in the Y. These two. All this comes down, 135 down, and we just found that, so this has to balance it. So I took the 135 minus the 72 to get the 62. I just didn't write it. So we're getting really good at this stuff. Right? Right. All right. So then time to cut, section time, right? I would cut through here for the first cut, and that would give me BC and HC, CH, however you want to call it. Right? And then put it back together and do another cut. Does that sound good? Which side did you work with?
A1.
AY side. So that makes this a vector, this a vector, and this a vector. So I'm not going to draw a new free body diagram. I'm just going to use this, but know that this side is now gone, right? And we're just going to use that left side. This is BC, this is HC, and this is HG, which we don't need. So we'll stick to finding the stuff that we need, and then we'll move on. Just looking to the left. All this shenanigan is gone. Including the 30, which I can't cover, but it's gone, right? That's the concept. So how do we find BC? And how do we find HC?
You do a moment at H.
True? How else could we do it?
Wait, HC you said?
Yeah, we need this one, the pink ones, HC and BC.
HC I did, the total of the FY.
Yeah. The thing I like about this is I look at BC and it's all in the X. And I look at HC and it's all in the Y. HG is also in the X. So X's we can't do anything with. So the moment's a good idea because we'll have to get there. But if we see the HC is all alone in the Y, go for that right away. So I'll do that. Some forces in the Y. Minus 45 minus 60 plus 72.1875. And then I drew, because method of section says just put them all in tension. Don't worry about it. So I'm going to write in minus HC, and that equals 0. Right? 45 down, 60 down, 72.1875 up, down, down, up, and then HC down is what I have. So HC moves to the other side. HC equals. It's like this becomes 105 negative, and then 72.1875 positive. I end up with a negative 32.1825. What's the negative mean?
That
that your direction is incorrect. HC does not go down. HC goes up. Yeah, so I wish I wouldn't have done it in ink, but I'll just scratch it out, which makes it look like a bigger arrowhead and point it up. Once you do that, then you go change your equation. HC now points up. So then this becomes positive and HC is in compression pointing into the point. So the math will correct your directional issues if you assume incorrectly. Then I think I heard Sean say do a moment at H. Is that right? So moment at H, we have three things dropping out and we can find BC. Great idea. Some moment at H. So we have to include all of them. I'll put BC in first. BC times 3 meters. And its rotation would be counterclockwise positive. 45 times 4 meters. And its rotation would be positive. So doing the moment here, got that one, got this one, I need this one.
Sorry, didn't you get, HC almost? It's supposed to be 32.8, 12 and a half. Instead of 182.
Oh, did I dyslexia it?
Yep, yeah,
Oh yeah, look at that, calculator.
yeah, blame the calculator.
It's, the calculator's right, blame me. Oh, 8-1. 8-1. All right. Thank you. And then we have that number, 72.1875, 72.1875 times its distance to H, which is a couple fours, 8. And its rotation is negative. All that equals 0. BC equals. What'd you get?
32.
132.5. Comes out positive, right? Points away its intention. Now we have BC and we have HC. We don't really care about HG. So we'll ignore it. And we put the truss back together and cut again. Other ways you could do it. Instead of 2 cuts, you could then jump to method of section or method of joints. And say, okay, I'll do analysis here because now I know this one, I know this one, I don't know this one, and I don't know this one. So method of joints would work also, just jump to C. So we'll start to combine these methods. Everyone see that? So we know this one now, and we know this one. The only one we don't know is this member here that has a Y component. So that Y component is going to be equal to HC. Could literally just trig that thing out. Or we can do another cut. So another cut would look like this, probably down through here. And on this second cut, vector here, and then a vector here. Actually, we're working with the left side, we'll put HG back in. Staying with this side over here. So hopefully you see this is the only one in the Y, this CG thing. So you could go for some forces in the Y and get the Y component of CG. Right? You could do that. You could do, what else could you do? A moment won't work here. A moment won't work here. Yeah. Without finding HG or CD down here.
Sure, find HC or HG.
I didn't find it.
7, and it like looked really wrong, remember that?
Oh, yeah. You remember that.
Yeah, it's good. This will be this one.
All right, so the second cut is here. I'm gonna do some forces in the Y for that second cut. Barely get it all on here. So I'm just gonna list them out. Plus 72.1875, that's this one. 45 down, 60 down. We're over here with the cut, so 30 doesn't show up, still looking to the left. Then I have this CY component, right? CGY. CGY. I'm gonna literally put that component in. I'm gonna put it going up and then set my equation equal to 0. That'll solve for the Y component of CG. So this becomes positive, goes to the other side, the 105. Looks like we're gonna be back to the 321825 number for CGY. 32.8125. Comes out positive, so this is the good direction. So I can now draw CG and CGY, which I know is 32.8125. CGX, which I don't need, but I do need an angle to solve this triangle. So this angle is going to be the height 3/4 inverse tangent. Oh, calculator went off. 36,869. So theta equals 36.869. Wow, 9. So then to get CG, opposite over the hypotenuse, sine theta equals 32.8125 over CG, where this is that C equals. Sine 32.8. $54. Yeah, would round to 54.69. Kilonewtons. Points away, it's intention. For final. So we have BC here, we have HC here, and CG 54.69. What's the book get?
What's that?
The book gets, wow. CG 54-7, that's the same. Intention, that's the same. CH 32-8, we get 32-8125, and BC 132-5. So we are good with the book. Well, that's always a good vibe. Two cuts. Yeah. Another one, right? 11. We want out of this one, we wanted this one, the vertical, and this one. Yeah. Anyone play the zero force member game with this? Russ? See a clean T?
Yeah.
Yeah, clean T right here. At H. Right? So if you draw the free body diagram of H, looks like this. With BH being the only force in the Y direction, it's equal to 0. So I like to draw these just to prove it to myself, so I'm not making bad assumptions. But that would be joint H. Everyone agree? The tricky one is joint B. And normally you follow zero force members, like you look to the other side. So we determined this to be 0 from joint H. So then it would be a good idea to do joint B and just draw it in its new form, which would be this. And again, I don't know directions, but it looks something like that. I don't know these directions of BC and AB, but I know they're in line. That's the important thing. These are in line at joint B. This is joint H. Right, it's this one right here. AB, BC are in line. So BH is the only force that heads off in this direction. And if I called this X and this Y, if I think about the Y forces, BH has to be 0 because there's no other force going in the Y direction. So I can conclude from this that BH is 0. Well, that's interesting. You can keep going, right? So now I know BH is 0 from the analysis of B. I go to the analysis of I. Joint I. No calculations here. I'm just drawing joints and thinking about, is there only one in a direction? This is CI. This is IJ. This is HI. So now I'm at joint I. And again, with this one gone, this one is zeroed out. It's a clean T. CI would have to be equal to 0. And that's one of the ones you're supposed to find.
How did we zero out BI?
We zeroed out BH here. And then BI we zero, this is BI.
Okay.
We zeroed out from joint B. Thanks. Just following that zero force member, right? Once you determine it here, then go to B and see if you can determine it there. And it works, it becomes, BI becomes 0 because there's nothing else going on at B. If we had a load here, like that, then this whole thing stops. Because now you have something else going on at B that's gonna load BI, but we didn't have that. Right? So you can just follow these things until it gets to a spot where you cannot rationalize a T. So we got here at CI. We went up to C now, this would become 0. So all of these zero out. But once we get down to here, there's too much going on. It's not a clean T. It's chaos. So that stops the zero force members. It happens on the other side too. 0, 0, 0, and 0. It just means all of the internal structure of this truss is not loaded under this loading condition. All right, so it's good to kind of think about zero force members before you start, because they can help. It only helped a little, solved one. But that'll help when we draw our section after we do our reactions. All right, which reactions did you use? AX maybe, AY? AX is equal to 0, is that true? No X forces going on, so AX equals 0. And how much is AY? Yeah, I see symmetry. So if you can see symmetry, you have 8,000 coming down. There's no other loads, just 8,000 coming down right in the middle. This has got to be 4,000. And that's got to be 4,000. So look for that. Little shortcuts. And then section it right through the 3 that they wanted. And I'm actually going to redraw the truss this time. That it's going to be my new section or my new truss. So A, blew it up a little bit, B, and this down here is I. 4,000 here. There is a member here. How far apart are these? 8 feet? 8 feet, 8 feet. Then I have this one in line going up, and that's BC. This one, which is 0, so I'm not even going to draw it. But if I didn't know it was 0, it would go in like that, and that is CI. That is IJ. Definitely getting more complicated. Ideas on how to go about this?
Find the angle of A.
This angle here,
Yep.
okay?
It'd be the same when you do the
The big one, the 12 height.
Yep.
And the 1, 2, 3 times 8, 24.
24.
So 12, 24 is what we have. And then inverse tangent. $26,565. Okay, now what? What's a strategy? What we want to know is all 3 of these, assuming that we didn't understand that that was equal to 0. Right? If we didn't see that, then we think this is loaded, the CI. What if we did a moment at A? What drops out? BC drops out, 4,000 drops out, what else? IJ drops out. They all go through that point. So if you do a moment at A, all you have is IC times 16, and that's got to be equal to 0. IC or CI equals 0. So that just proved it. That our zero force analysis up here is true. It's a moment at A, it's got to be equal to 0. BC goes through the IJ drops out. We just left with CI times distance. That's cool. Now what? How can we get IJ or BC? I like moments. I kind of do a lot of them.
BC, what I did is, I found the BCY, which is gonna be the same, as the pound or the force applied there.
Yep,
And then, I did which is 4,000 divided by sine
Yep.
theta, and now you get BC there.
yep. So what Jorge is saying he did is sum forces in the Y. That's a great strategy because IJ is all in the X. It's not gonna come into this equation. So that means we have plus 4,000. And we have probably not up because these two, right, have to oppose each other. So right there, I can see, oh, I bet BC comes down, it has to. Right, but that component right there, BCY, is in the equation. So 4,000 up, BCY. If you just see that, you don't have to write the equation. I'm okay with that. But if you don't see it, write the equation and hopefully then you will see that BCY has got to equal the 4,000. So that means, okay, let's just draw BC, right? BC and the 4,000 and BCX and our angle, which we have for 26, right? And we can solve for BC. So I'll use the sine again, sine of 26565 is equal to 4,000 divided by BC. BC equals. Again, it's a division thing, 4,000 divided by the sine of 26. $89.44.
I think the book rounded off to 40.
Yeah, does some rounding, that's for sure. Pounds, and it points into the point, so it's compression. Love it. And looking at this, what's IJ equal to? Equal to the X component of BC. Yep. So this and IJ are equal to each other, these two. So we can just use this same triangle. Cosine this time, right? Because we want the adjacent side. And the 4,000, so.
Opposite of just using the 4,000.
I was using the 4th. Oh. I was using this and BC,
Oh, okay.
so. Because now I know BC, right? Yeah. So that's how I was doing it. So I probably should write it out so I don't make a mistake. Cosine 26.565 equals BC X, which is also the same as IJ over 8944.27. Tangent would work too, so either one. Oops. Sorry. 8,000? I J equals 8123. That's pretty rounded. And then which way does it point? Yeah, it points out. Tension. Method of sections. Don't. What did the book get? This 11? Yeah. 11, the book gets BC 8944. Good. IJ 8,000. Good. And 0. CI 0. Very good.
As I said, my book is rounded up to 8940.
Oh, did it? Not 4-4?
Yeah, I don't know why.
Oh,
they
that's
rounded up.
interesting.
Yeah.
Yeah.
But I stayed with my math because I double checked it and I said
Very good. Very good. Turn him in. Turn him in, turn him in. We'll talk about frames. We'll take a little break. 5 minutes or so. All right, frames, first frame. So how do we know it's a frame? Because it's not a truss. What was a truss? Triangles. Straight members. This is straight members, so that's good. Trusses, the loads are always at the connections for trusses. They're not in between the joints. This one clearly has a load between two joints. This is a link. A to, what they label that? A to B is a link. This must be C. Yeah, all right. So this is good to recognize these links, but it has a load on it, right? An intermediate load. So it makes this a multi-force member, and DBC is a multi-force member. That means these members don't just carry load straight along their line of action. They actually have some kind of bending load on them, right? It's a frame, not a truss, for those reasons. So when you draw them, you're going to want to draw them with some kind of depth or thickness. And then also just keep individual members, like obviously this is one member across here. So that's the way I drew it. Because you want to keep track of like where the connections stop and go, right? Trusses, we just use lines a lot of times for trusses because we know every member stops at every joint, right? But frames can be different, like this one goes right through a joint. So free body diagram for frames, your system or procedure is still going to start with a free body diagram. And that means leave the frame together. leave it together and just draw the free body diagram. So pull out the pins, put in the reactions, take a guess at the directions. So at D, we have a pin. How many reactions does a pin get? It gets 2. X and Y. D, Y, D, X. There's a pin at A. How many does a pin get? 2. Again, you're just gonna guess at the directions A, Y, A, X. So free body diagram, step 1, solve for reactions is step 2, so the steps haven't changed yet. With frames though, you typically are not gonna be able to get all the reactions, but you should be able to get a couple. So get the ones you can. What reactions can we get? Again, leaving the frame together, right? I've not taken anything apart. What can we get? Can we get the Y's? Can we get the X's?
The Y's? No.
Cannot get the Y's. Agreed. We can get the X's though, right? How do we do that? We have DX and D or AX and DX. How can we get these? Well, we have 3 equations. We can sum forces in the X, but there's 2 unknowns. Just do a moment. Yeah, where do you want to do the moment? Moment at C? We can do it out here. It's crazy. More things drop out if I do it here, right? 2 drop out. Only 1 drops out here. Or here, 2 drop out, 3 drop out. 1, 2, 3. Do it here, 1, 2, 3 drop out.
D.
All right, let's do D. Moment at D. What are all the moments that create, all the forces that create moment about D? We have AX times, do we know that distance? No, but can we find it?
Yeah.
Yeah, because we know 8 here, and we know 40 degrees, right? So we could say what, tangent 40, because I want to use opposite over adjacent. Yeah. And I'll call it, I don't know, I'll call this D. D distance over 8. And this gives us a D distance of 6.713. 6.713 feet. 6.713 feet. The rotation that I chose is this way, right? Counterclockwise plus. What else creates moment about D? Yeah, 2,500 times 4. Rotation negative. Anything else? 3,000. Times 12. Rotation negative. Nothing else. When you're at this step, this solving for the reactions, notice I did not take point B apart. You're gonna do that by accident. Don't do it. There's no forces here. If you leave it together, if you leave a point together, you don't have to account for the forces. It's still together, right? So I've left the frame together when I solve for the reactions. That's super important. What do we get for AX? See if the engineering firm can come up with a number here. To move to the other side, become positive. Six, 8, 5, 2. Boy, I get 5, 8, 3. I use the whole number here. Yeah. Pounds. And it's a reaction, so it's just pointing in the direction that we assumed it here. That's AX. What's DX gotta be equal to? The only other force in the X direction, AX, yep, and it's gotta point the opposite direction, correct? Gotta point to the right, and it's also gonna be 6, 8, 5, 2.583. So now I know AX and DX. We got two of the reactions. We cannot get the Y's. There's no way to get them. You can sum moments anywhere you want. You're gonna end up with two unknowns in it, dy and ay. Right? Or you'll sum a moment here and they'll both drop out. So there's just no way to get the Y. When they line up like that, you can't get the Y reactions. It's not possible. So you get as many as you can in the get reactions step. And then step 3 is you take it apart. Take frame apart. All right, here's the hot tip. When you take it apart, we're going to draw separate free body diagrams of each piece of the frame. And the easier one to solve, because then you look at it piece by piece, the easier one to solve is always going to be a horizontal or a vertical member. The one on an angle is just going to be more complicated, more angular distances defined for moments, those kind of things. Okay, so frames, free body diagram, solve for their actions, then take it apart. When you take it apart, I'm going to draw both down here. You want to keep members in their angular position. So here is AB. And its loads, as I know them, 2,500 and an unknown AY and a known AX. 6, 8, 5, 2.53. And when you take B apart, that was a pin, right? It was pin connected here. So it gets 2. And you want those to balance with everything else going on that member, because that single member would have to be in equilibrium. All right, so I put in what I know. I'm guessing at AY here. So I guess at BY opposite of AY, because that's how this piece would be in equilibrium. Okay. And then taking the frame apart, then here is the lower member. And this was a total of 8. And this is point D. So I know I have dy. I don't know which way dy goes, but I'm just putting it in. dy. I know which way dx goes, and it goes into the point from our analysis up here. And it is 6, 8, 5, 2. 0.83. I know I have this 3,000 out here. This is point B, this is point C, right? My notation, boom. Now, when I put the forces in for B, it's a pin, so it gets 2. And it needs to be opposite of the other point B. So when the point B's come back together, they're in equilibrium. Everything fights each other. So if you draw BY down here, you have to draw BY up here. If BX is to the right, then this BX has to be to the left. So when point B comes back together, it all equates to 0. Okay, that's very important. Of course, you use whatever you know, like we know the 6852 going in, right? BX must fight that. It's the only 2 in the X direction. So BX has to be equal to what? Yeah, 6, 8, 5, 2.83. Notice I'm kind of focusing in already on that horizontal member, right? This is harder to figure out, although there is only 2 X forces here, correct? Yeah, so this one also is clearly 6, 8, 5, 2, and it has to be BX and BX. They're the same. They have to be the same. Different. Oh, 583. Gosh dang it. That's really getting me today, isn't it? I think I'm just extra tired. 583.
And
Wow.
every combination of.
Wow, that's terrible. Almost did it again right there. So we're getting there. What?
Why does it trial now?
Great. That's great. We still don't know BY and AY, right? And I believe the problem says determine what's going on at pins A, B, and D, right? So this is pin B, it's pin A, pin D. They want to know everything going on at those locations. So we need BY and DY, and we need AY and BY there. So still have that to do. That's where we focus in on this horizontal. When you do these, you literally, each member has to be in equilibrium all by itself. So you can ignore the other member while you're working on a member. So here, how can we get BY and DY? Absolutely. So that's where we're going to use all of our strategies, just looking at this horizontal member. We did a moment here. What drops out? Well, everything at B, and what else? DX drops out. BY drops out. BX drops out. We're left with DY and 3,000 for a moment. Again, pretty easy on the horizontal member. Moment at B, moment here. 3,000 times. So when we're doing that, we can just look at that one member. 3,000 times 4. So that gets clockwise, negative. And DY times 8. And that one looks like it's also clockwise, so that's a problem. You have 2 clockwise rotations. But we'll let the math solve us out, set it equal to 0. This goes to the other side, becomes positive. We're gonna end up with a negative number. DY equals 1,500. Negative. And we know what that means. Negative number means we have a bad direction. So go change it. dy does not point up, dy points down. That puts it positive here for the rotation, and that puts it positive for the answer. So you want to change the direction. Hence, we work in pencil, and then you can change the signs in the equation, and you get your positive number. If dy is 1,500, then by is 1,500. This also equals by. And then you can transfer it to the other member because by has to be by, 1,500. Right? Then that transfers because now we have 2,500 down, 1,500 up. We need another 1,000 up. Ay equals 1,000. So you jump back and forth between the members. Yeah.
Who was that group of the A2B? It shows that the pointing down. Should be up.
Here?
Yeah.
No, because it has to be equal and opposite. Equal and opposite. So when that pin comes back together, it's 0.
So wouldn't
2,500 down. 1,500 down. Oh yeah, bad math in my head. It's gotta be what? Yeah, 4,000. Good catch. 2,500 down. 1,500 down because it flipped over. 4,000.
I feel opposite over here.
Wait till you get like 6 members in a frame. Then you're jumping between all 6 members and transferring forces through pins. Gets confusing. But that's the strategies. Leave it together in the beginning. So I'm really emphasizing that. Don't take it apart. Leave it together to do your reactions. Then take it apart and draw separate free body diagrams that communicate to each other. And that's what this B thing is, right? When you take it apart, point B and point B, they're the same loads, but they're oppositely directed. And you may not know which way they go on one member. So when you draw it in, just oppositely directed in the other one. And then when it tells you that it's incorrect, then change it up through the system, right? Start with your horizontal vertical. I gave you a pretty easy one for homework. It's this one. It's a horizontal and vertical member. So this shouldn't be too bad, but just practice it. So I gave you, already threw it away. 2 of them. 12 and 16. So 12 is a truss. 1 more truss, and then 16 is a frame. Questions on this one? Anything? There's a lot. It's a pretty simple frame. They get complicated, as you can see in the book, as you look through. There's like 48 problems in this chapter, meaning that they want us to do a bunch of practice. So. When you have frames that have like multi-angle frames, like this one appears kind of simple. It's 2-member frame, but neither one's horizontal or vertical. So it's pretty difficult frame to solve. Lots of strategies there. All right, good. All right.